Hello everyone and welcome back. In this video, I'm going to teach you the squeeze theorem. I know when I say theorem, you guys gonna start panic, but don't panic. This is a very easy theorem to understand. Okay. All right. So I will try to explain this in three ways. Okay. Let's start with an example. Rather than just giving you the theorem, I will start with an example. So think about the sequence negative 1 to the n over n. And you want to know whether this is convergent or divergent. So the thing that we need to do is we need to find the limit of this sequence. Now I know that you guys know the limit of this sequence, but pretend that you don't know. Okay, pretend that this is a very difficult sequence to find the limit. Okay, so let's write this again, negative 1 to the n over n. Okay, finding the limit of this guy is a very hard thing to do. Okay, right, now rather than finding the limit of this sequence directly, I'm going to do something else. What I'm going to do is, let's write several terms of this sequence. Okay, so the first term is going to be negative 1, next term is going to be half, the other one is negative 1/3, the next one is 1/4, so and so on, right? So the terms of the sequence are switching between positive and negative values. Okay, anyway, so I wrote several terms of this sequence. Now what I'm going to do is, I am going to create a new sequence. A new sequence such that this new sequence is greater than or equal to the given sequence. Now how can I construct such a sequence? It's super easy to do here. See, I have these negative terms, right? I'm going to turn them into positive and I'm going to keep others. So I'm going to turn negative 1 to positive. So I'm going to keep 1. I'm going to make it 1. I'm going to keep half. Okay, because we can be greater than or equal. So some terms can be equal. So let's use that fact. Negative 1/3, I'm going to turn that to 1/3 so that it's greater than negative 1/3. 1/4, I'm going to keep that. So I constructed a new sequence where this new sequence is greater than or equal to the given sequence. Now what's the general term of this sequence? 1 over n, right? Okay, nice. Now what I'm going to do is, I'm going to create another sequence. Now this time, this new sequence is smaller than or equal to the given sequence. How can I construct such a sequence? What do you think? Now I'm going to turn these positive terms negative. So I'm going to keep negative 1 because I can be equal. So I'm going to turn half to negative half. I'm going to keep negative 1/3. I'm going to convert 1/4 to negative 1/4 and so and so. Alright, so what's this new sequence? Negative 1 over n, right? Okay, so what did I do here? I created two new sequences where one sequence is greater than or equal and the other sequence is smaller than or equal. Right, now these two sequences has something special in common. The first thing is, finding the limit of these two sequences is an easy task. What's the limit of 1 over n? 0. Super easy to do. When n goes to infinity, the limit is 0. What's the limit of negative 1 over n? Still it's going to be 0. Okay, so that's one thing. Okay, finding the limit is super easy. Okay, and the other thing is, guess what? The limits are same. Okay, they have the same limit. All right, so based on that fact, can you guess what's the limit of the middle sequence? It's also going to be the same limit. It's also going to be 0. So the limit of the sequence when n goes to infinity, limit of negative 1 to the n over n is 0, because the limit of the sequences that are on the sides are same and are same. Okay, all right, so this is what squeeze theorem tells you. Okay, if you have a sequence where finding the limit is difficult, then find a new sequence which is greater than the given sequence, find another sequence which is smaller than the given sequence. If the limit of the boundary sequence, if they converge towards like alpha to the same number, then the middle sequence is also converging to the same limit. Okay, so that's what squeeze theorem tells you. Now understand the word squeeze. The reason that they call this theorem the squeeze theorem, because in a way the sequence in the middle is squeezed by the sequences on the boundary. Think about this. The sequence negative 1 over n is pushing the sequence negative 1 to the n over n from below. And at the same time, the sequence 1 over n pushing the sequence here in the middle from above. So this sequence in the middle get squeezed, right? It's screwed basically. Now this is like in a horror movie, like imagine like in a horror movie, there's a person inside a room where this person is trapped inside the room and the walls from two sides are pushing towards each other. I know this is gross, but the person in the middle is screwed, right? So that's what happens to this sequence. So that's what squeeze theorem tells you. Now what we're going to do here is we're going to properly define the squeeze theorem. I'm going to give you the proper version of the squeeze theorem, and let's look at another example and a pictorial explanation of this, okay? Alright then, so here's the fully stated squeeze theorem. Now in the squeeze theorem, you're working with three sequences, right? So suppose that xn, yn, zn are three sequences such that, okay, the sequence zn is greater than or equal to the sequence yn, sequence xn is lower than or equal to the sequence yn. So the sequence yn, the sequence in the middle, that's the important sequence. That's the sequence we want to find the limit of. But it's something hard to do. So let's think like that. And the other thing is that, so you have this inequality, you have this relationship, okay? Alright, so in other words, you have the sequence yn, now you need to construct two new sequences zn and xn, such that the limit of the sequence xn and zn are same, okay? So the limit of these two sequences on the sides, they are same. If that happens, if you are capable of coming up two sequences like xn and zn where the limit is same, then the sequence of the middle sequence, not the sequence of the middle sequence, the limit of the middle sequence yn is also same as the limit of the sequences on the boundaries, okay? So the limit of all these three sequences are same, hence the sequence yn is also convergent. So that's the idea. This is the correct statement of squeeze theorem, a very simple idea, okay? Again, the sequence yn gets squeezed by sequence xn and zn, so you need to find two sequences that can squeeze the sequence yn. All right, so let's do another example and let's actually see this squeezing idea from a picture as well at the end of this video. So let's go to an example. Alright, so here's another example before we go to the picture. Now, pretend that this is a sequence where finding the limit is very hard, sine n over n. Now, what I want to do is I want to find a sequence greater than sine n over n and smaller than sine n over n. Okay, so how can we find such a sequence, such two sequences? Well, we know something from calculus. We can say sine theta is between what values? What do you think? Sine theta is between -1 and 1, right? So sine n, think about this. Sine n, let me erase this. Okay? So sine n is definitely then between -1 and 1. I guess you agree. Okay. Now we have divided by n, and remember n is a positive number. N is the position of the sequence. So I'm going to divide by this positive number n, the entire inequality. And the inequality doesn't change again because we are dividing by a positive number. So now we have sine n over n in the middle. Wait a second. Now we have 1 over n greater than sine n over n and -1 over n smaller than sine n over n. Okay. So what do we need to do? Well, now we need to find the limit of 1 over n. What's the limit of 1 over n when n goes to infinity? 0. What's the limit of -1 over n when n goes to infinity? Well, it's again 0. We know that. So this sequence converges to 0. This sequence converges to 0. So the sequence in the middle is also converging to 0. So the sequence in the middle also convergent. So the limit of the sequence, limit when n goes to infinity of sine n over n is 0. Okay, by squeeze theorem. So this sequence is a convergent sequence. See, again, it's very easy to use the squeeze theorem. Now let's go to a let's go to Mathematica and see this from a picture. See this example from a picture. After that, in the next video, I'm going to do hard examples. I'm going to show you 2 hard examples from squeeze theorem. Alright, so here's my attempt to explain this squeeze theorem using a picture. Hopefully it makes sense and this works. Let's see, let's give it a try. Now we already know the sequence sin n over n. We solved it using the squeeze theorem. That's what I have used here to explain. We know sequence negative 1 over n is lower than sin n over n, and the sequence 1 over n is greater than sequence sin n over n. Okay, so let's look at these sequences using a picture. 3 sequences using a picture. Now here's what I ask you to do. Look at this picture. So in green color we have a one sequence, in orange color we have a one sequence, and in blue color dots you have another sequence. Guess what those sequences are? What is sin n over n? What is 1 over n? What is negative 1 over n? Can you guess? Now if you can guess correctly, then you have understood this squeeze theorem. Now the sequence in this green color dots, that's 1 over n. That's above everything. Sequence in orange color, that's negative 1 over n, under everything. And what's in between? See these blue color dots, they are trapped in between this green color and orange color dots, right? So that's sin n over n. It's all over the place. Okay, the sequence sin n over n is all over the place, but still smaller than 1 over n and greater than negative 1 over n. And what's going to happen is that this blue color sequence, if you can see blue color dots, they are getting squeezed between this green color and orange color sequences, right? This green color sequence approaches to 0. This orange color sequence approaches to 0, meaning both of them going to run into each other, right? Going to overlap into each other. While these blue color dots, unfortunately for them, like they are trapped between these two guys, and these two guys going to run into each other. So then the blue color dots are screwed, right? Which means the limit of all 3 sequences are same, okay? Alright, so that's the squeeze theorem. Rather than finding the limit of this all over the place sequence, you find a sequence greater than this weird sequence and a sequence lower than this weird sequence. And if these 2 sequences on the boundary, okay, from top and above, if they approach us to same thing, then what's in the middle, this weird sequence, gonna overlap to that as well, gonna fall into that as well. So that's the squeeze theorem pictorially. Hopefully it makes sense. In the next video, let's solve some challenging problems from squeeze theorem. Okay, so hopefully I'll catch you in the next video. Thank you very much.